In this video, we're going to start looking at what happens to circuits is where we're going to get to eventually, but we're going to start off by talking about what happens to systems consisting of more than one coil when there's a changing current in one coil and what happens to the flux through that coil and the other coil. So instead of just talking about it, let me actually draw something. So let's take two coils. Here's coil 1, and here's coil 2. And I've drawn them as just, one loop, but we'll assume that these could be, have any number of loops or any number of turns, and so they could truly be coils, as I said, instead of just saying loop. So we'll say that loop 1 has a certain amount of turns, and 1, loop 2 has a certain amount of turns, and 2. We'll say that possibly there's a current I1 here, and there could be a current I2 here. Whether or not we drive the current or the current is driven by a changing flux just depends on how you set it up. But in general, there could be a current in coil 1, current in coil 2, N1 turns in coil 1, N2 turns in coil 2. Okay, fair enough. Now, let's drive a current in N1. So let's connect this to some voltage source, and now we're driving this current I1. Okay, what happens? Well, I1 produces a magnetic field. Magnetic fields propagate out through space, right? Let's see what that looks like. At the very center, we know what it would look like. It would be something like this. And then it's gonna, go out from there, as we know coils do. But the point is, there will be a flux through the second coil due to the magnetic field of coil 1. Fair enough. Well, what happens if we now change I1? We either ramp it up or ramp it down or turn it off or turn it on. What happens? Well, there's now a changing magnetic flux through coil 2. And so we induce a current in coil 2. We induce an EMF which produces a current. Okay, well, what happens then? Well, that current produces a magnetic field, which then has a flux through coil 1. And if this is changing, which it will be if we start it running, it ramps up. Or if it changes in any other way, it will induce an EMF in coil 2. And so you see you have this back and forth relationship here where I1 affects I2 and I2 then affects I1. We're talking about the idea of some mutual inductance. And I don't do a whole lot with mutual inductance in this course. We're going to do a little bit with self-inductance, which we'll talk about in the next video. I'm just going to briefly go over this. The concept is here. I'm going to introduce you to some of the terminology, and then I don't do a whole lot else with it in this course. If you go on to advanced circuit classes, of course, it becomes really, really important. Because if you have two circuits sitting next to each other and one of them is turning on and off, and well, that induces problems or could induce problems in the other one if you don't have them isolated properly. So I want you to be familiar with it. Let me just define what we call the mutual inductance of this system. We will define mutual inductance M. Well, we'll define the inductance of one coil. Let's do that. Let's say the mutual inductance N2 due to 1, right? Inductance of this due to 1 is going to be equal to the number of turns in coil 2 times the flux through coil 2 due to coil 1. That's what the order of subscripts means, right? The flux through coil 2 due to coil 1. That is, there's a current in 1 producing a magnetic field from 1, which is passing through 2. Magnetic flux through 2 due to 1. And that's going to be divided by the current producing that magnetic flux. And so this is a definition of mutual inductance. I should point out the unit of this is the Henry, after a physicist who discovered EMF independent of Faraday. But the units are Henrys. But of course, as soon as I do this, mutual inductance means there's a back and forth. So I can just as easily define the mutual inductance of coil 1 due to coil 2. And just by changing out my subscripts, I can come up with that. The number of turns in coil 1 times the magnetic flux through 1 due to 2 divided by the current producing that flux, I2. All right, so here's the good news. It can be shown that these two are actually equal, which probably doesn't surprise you too much if you really think about it. If one system is affecting the other, there has to be something in those two systems which relates them, and it turns out it's the mutual inductance. So that enables us to just drop the subscripts and say that the mutual inductance of this system is equal to either one of these expressions, which is equal to N1 phi12 over I2. That is mutual inductance. Okay, well, what do we do with that after we have it? Well, what we really want to do is be able to characterize an EMF through either of the an EMF induced in either of the coils simply, and as it turns out, there's some simple expressions for that. The EMF induced in coil 1, remember we have a coupled system here. I don't have a coil 1 unless I have a coil 2. It's going to be minus times the mutual inductance di2 dt. This should make some sense. What is producing the change in flux through coil 1? It's the change in current in the other coil, right? So di2 dt is just how the current in the other coil is changing, which through the proportionality constant of the mutual inductance then gives you the EMF induced in coil 1. Of course, E2 will be minus M di1 dt. So these are some relatively simple expressions, and that's as far as I'm going to go into this. Like I said, I don't do a whole lot with mutual inductance. That does not mean it's not important. It just means that you will get enough of this in more advanced classes if you need it. For our purposes, the more important thing is self-inductance, which is how a coil and the changing current through a coil induces an EMF in that same coil, which we're going to look at in the next video.